Most of what I'm going to talk about today is motivated by two theories that have been developed in parallel over the last couple of years. And well, the first theory starts with a three-manifold M, maybe oriented, and with a boundary being a torus. Okay, and with such an object, you associate a type D module. Okay, so it's here D of M, given some, which depends only on some parameterization of the boundary of that manifold. Okay, so this is border theory due to Lipschitz, Oswald, and Thurston from around 2008. And then 1 or 2 years ago, I think, a group of authors, namely Jonathan Hanselman, Jake, and Liam Watson, Sherbrooke, and noticed that these invariants can be represented by immersed curves on the surface. And the surface is this torus minus a special point. Okay, so that's the first theory. And the second starts with a 4 in the tangle. So tangle with 2 open components and maybe a number of closed strands as well. And that tangle lives inside the closed 3-ball. And with that, you associate an algebraic invariant, which are called the peculiar modules of tangle. So this is from my thesis. And again, you notice that these can be represented in some examples, like all that I know. You can represent them by immersed curves on the surface. It's not this surface, but it's the boundary of the 3-ball. So it's S2 minus 4 marked points, which are the endpoints of the tangle. Okay, and if you write down like this, then you might wonder, is there some general theory behind this? Okay, and the purpose of today's talk is, well, it's an attempt to lay the foundations of, well, yeah, such a theory. Okay, so we start actually at the end. So we start with a general surface. Okay, and then given some extra structure on the surface, which I'll explain in a moment, you associate with that surface, you associate a quiver. And from that quiver, you get an algebra, an A-infinity algebra, which I denote by A-infinity. And from there, there's a standard procedure how to associate an A-infinity category. So an A-infinity category of twisted complexes. And the way that you think about these twisted complexes is you think this category encodes algebraically the Fukaya category, i.e. the Lagrangian intersection theory on that surface, on S, where S is this surface. Okay, and this was done by Haiden, Katzarkov, and Kontsevich in a paper from 2014. Okay. Now, I don't really want to say anything about this today. Well, there are 2 reasons. Well, first of all, you can just go and read this reference, and secondly, I think from a sort of Heegaard Floer point of view, it might be better. There might be a better way to encode this Lagrangian intersection theory. And the way that you encode this is by, well, you replace this category. You replace it by a category of curved complexes. Okay, where does that come from? Well, it comes, so you again start with a quiver, with a surface. You get a quiver, take the same quiver that you use down here, and you associate with that slightly different algebra. Okay, so this was an A-infinity category, an A-infinity algebra. okay, the differential vanishes, so it's actually also an algebra. But you need the infinity structure to define this category. Okay, and here you just have an usual category, usual algebra, and from there you do a very similar construction down here, and you get a differential graded category of curved complexes. Okay, and I will spend the first half an hour or so of the talk describing this construction in, I hope, sufficient detail to understand what's going on. Okay, and then the remaining part, I will try to well, sketch what we know about this connection here. I mean, there should be some connection, well, first of all, because of these two examples, okay, but also there are two functors that you can construct between these two categories. So I can construct these two functors in my thesis only for this surface, but then later I realized actually you can define that in general. And I used them in my thesis to actually show that when you start with a tangle, you get this algebraic invariant. And then you map it through this function, and if you believe this, then you get some immersed curves on this surface. Okay, but actually proving that, well, I suspect that these two functors set them an equivalence of categories after the homotopy, but proving that is, yeah, rather hard, I guess. I mean, it's painful. And I've given up on this part, this approach here, for the time being, because I think that it might be just easier to prove this connection directly. Okay. Right, so I think that's the plan for today. Do you have any questions? Okay, good. What happened?
You.
Okay, great. So let's start. Well, first of all, I need to tell you what these surfaces are. Okay, so we start with marked surfaces. Marked surfaces pair S, M, where S is, well, it's an oriented compact surface with boundary and no closed components. Okay, and M. M is a marking on the boundary of that surface. So M is an embedding. It's a one manifold that sits on the boundary of S. Okay, such that every component of the boundary has some marking on it. I.e. that it's M subject. Next, we define the extra structure that we need on this surface to get a quiver. So an arc on such a surface. Question?
M is a bunch of arcs on the
M
boundary.
is yes. So it's you put a marking. You color the parts of the boundary. In this case, in green. I will draw an example in a moment. I hope that will clear. Okay, so what is an arc on the surface? Well, it's an embedding of an interval on the boundary into this pair from M, such that the class that you get in I1 of S from M is non-zero, i.e. you can't contract that curve. Okay, and finally, an arc system. Should I draw in red? What is that? That's just a union. Arcs. It's a union of arcs which are pairwise disjoint. What else? Right, and that are pairwise non-topic. Right, and also finally you want these arcs in your arc system to cut the surface into contractible components, i.e. that S minus A. Okay, and this is just a disjoint union of disks. Okay, so that's an arc system. That's the data that we need to start with. Okay, now let's try to look at some examples. Can I erase this?
You have a disk with whatever marking on the boundary. The empty set is an arc system.
The empty set will be an arc system. Right. So yes. Well, I mean, this is a degenerate case. Maybe you want to have one arc.
And that is regardless of how many connected components of M I have on the boundary.
Again?
That doesn't depend on how many connected components of M I have on the boundary.
No, that doesn't matter. Yeah. Okay, so I want to in the entire talk, I want to focus on two examples, namely the two examples that I just erased. So the first surface I want to look at is S equal to the torus minus a point. Okay, what does it look like? Well, we identify opposite edges. Okay, and then so this is part of the boundary. Okay, so I can put a marking on this here, and maybe I don't mark this region. Okay, and then I need to draw some marks on this surface. Okay, that cuts this into disks. Okay, so in this case, I need two arcs. Just want two arcs on there. Okay, and so that gives me an arc system. Okay. Right, and conditions are satisfied, and yeah, that's the picture that we draw for this surface. And then the second example is the four-pointed sphere. Okay, the picture that we draw in that case, well, in this case we want to maybe mark every part of the boundary, so we just have these four punctures. So I'm drawing this sphere in the plane plus the point of infinity, and now I just add some arcs. Okay. So I have two faces here, a face at the front and a face at the back. So those are the two marked surfaces that show up in these two examples. Okay. What's going on?
There's an electrical box down here.
Right.
So there's also a little sensor that tries to turn the light off.
Right, so I think it's time to now define the quiver. So I want to keep this board for these two examples. Okay. Definition. So given such an arc system, given A on some marked surface, we define quiver to as follows, with vertices given by A. Okay, so every arc in the arc diagram in this arc system is a vertex, and then with arrows defined as follows. So those are boundary-oriented components of the marked boundary minus the endpoints of the arcs. So boundary-oriented of the marking minus the endpoints of A. Okay, so there's an illustration for this. So we have part of the boundary looks like this, and then we might have two arcs. Okay, and then we choose some convention on our boundary with orientation. And so this would be, let's call this row. Let's say this is L1, this is L2, and then that would correspond to an arrow from L1 to L2. Okay. Right, so what does that look like in... so what does that look like in our two examples? I mean, up here we have two vertices, right? This arc here and this arc here. So we have a graph with two vertices, and then we have a number of marked components. So let's call this row 1, row 2, row 3. They're oriented like this. Okay, and maybe I want all parts of the boundary to be marked for this example. Okay, so let's do this. Or maybe, sorry, I think that's your convention, right? Okay, so 0. Right, and now we draw these arrows. So there are 4 arrows. So we go from here to here by row 1, then come back by row 2, and then let's go in the other direction by row 3, and then row 0. Okay, so that's what this quiver looks like. And in this example here, well, there we have some more components. So there I label these front components by PIs. Okay, and components on the back by QJs. Okay, and now I get a quiver with, okay, let's also label these 1, 2, 3, 4. So I get a quiver with 4 vertices. 1, 2, 3, 4, and then I have a number of arrows between those. Okay. So here on the front, sorry, do I have, yeah, I've chosen the wrong dimensions. Sorry. Yeah. That was fine. No. Okay, I mean it doesn't really much under the convention, but yeah, now it should make sense. Okay, so this is P1, P2, P3, and P4, and then we have the Qs on the other side. Okay.
Yes.
Questions? Sorry.
So I guess I missed this earlier, but so each
arc is supposed to meet the boundary of M or something like this. So
Yes.
what is so M is like a
So in these two examples, M is everything. So it doesn't really matter where it is.
yeah, but M also
And,
oh M minus. I'm sorry, I missed that part. Yeah, I see. So the arrows are components of M minus.
yes, yeah. So they are. Yeah, I mean, right. Okay.
No, no,
so if I have some, if the marking stops here, then this short path here is set to be equal to 0. Maybe that's what's confusing. Yeah, I didn't say that, but I did want that one. 0.
I guess I don't quite, so I don't understand. So, so if M is an integral or an arc, I mean, if M is just a line, then you're going to get.
Yeah, I mean, if there are
You
no
better
arcs,
get-
if there are no arcs, then I just ignore that. But then,
You,
yeah, I mean, I didn't say that here. That might-
you only boundary or orient the components of that.
Boundary
that
oriented.
contain,
Boundary oriented. So it's
Yeah,
it's the
you're-
components of M minus the endpoints.
but that's not quite what you read, is it? It's only the ones that contain
That
two endpoints.
there's only contain. Yes, sorry.
But you
yes,
want to have simple paths between
Yes.
endpoints of
Yeah.
arrows.
yeah, exactly. That's not quite precise.
So if you deleted edge 4, red edge 4 in this example,
If I
that would
deleted,
be a valid
that
marking.
would be a valid.
Could you draw the quiver associated with that? Just
Yeah, sure. I mean, then you would erase this part here, and then instead of getting this P, you would get a loop for 1, and you would also get a loop for 3. Yeah, any more questions? Okay. Okay, so we now have the quiver, and I guess the next thing I should tell you is what the algebras look like. Okay, so definitions given this this Q of A, we define these algebras as just the free quiver algebras modulo some relations. Okay, so define A infinity to be the free quiver algebra modulo some relations which are denoted by R infinity. Okay, great. And A CC VF Q modulo R CC. Okay, great. So now what are those relations? So I guess you can explain those also in terms of these pictures. That's the easiest way to see those. So given some arc Li, okay, what does it look like? Well, it looks like this. Okay, maybe those are not components here are not marked. Okay, but in general it looks like this. Okay, now then I have some arc elements. Okay, some of these might be 0. Okay, but it doesn't matter. Okay, so now I just introduce some notation for these. There are 2, maybe 1 bar. So I now want to introduce some relations on here. Okay, and what I do is I just say, okay, we can compose these four elements in various ways. But if I start with this part here, I can go either this way or I can go that way. Okay, so in this for A infinity, I said this equal to 0. Okay, so that's for A infinity, or for R infinity. Okay, so R infinity, if I write down what the relations are, then it's bound by these elements AI1 bar AI2, this part here, and then also this, sorry. Right, composed like this. So that's AI1 AI2 bar. Okay, and do this for all I. Okay, so that's R infinity. That's those relations. And for these relations RCC, and what we do is we just set these compositions equal to 0. Okay, so so RCC, what do they look like? They look like this, and then like this. I'll do this for all I. Okay, so now let's look at the two examples and work out what these two relations tell us. Okay, so in the first example, let's try to work out infinity. Okay, what does it look like? These relations tell us that if we go along to some arc, okay, and then go across the arc, and then go, yeah, and then we have one option left. Okay, so then we set those elements equal to 0. So we set I rho I plus 1 rho I equal to 0. Okay, and for RCC, what do? We set those compositions here, but if I walk over here, then I get this. Okay, so there I said rho I plus 1 equal to 0. Okay, so in this example, for this particular surface, these two algebras are actually the same up to, yeah, I mean they're opposite algebras also. Okay. But that's not true in general. So in this case down here, there we get R infinity is equal to, yeah, what do we get? Here we said compositions of p's equal to 0. Okay, so p I minus 1 pi is set equal to 0, and similarly qi plus 1 qi is set equal to 0. Okay, and RCC, we said compositions are very, for RCC, we can't walk around the ends these functions. Okay.
I don't know.
In the first example, is it the other way around? The eyes?
Oh,
He's composing.
maybe I'm composing the.
Okay, he does it backwards. Okay, okay, thank you.
Well, I don't know.
It goes from
Yeah, what is the
right
bar?
to left.
Yeah, so
Okay, okay, sorry.
good man. But what is the bar and the I?
That's just, I could also call them B's. I just labeled those algebra elements.
So that's just his name for the.
That's my name for these algebra
Right,
elements.
yes.
It doesn't have any meaning.
They're not related to the ones without the bars.
No, vertical bar. The
For all
yes,
I.
the cat.
Sorry, yeah, I mean.
So that's the starting vertex.
So,
No,
no, that's
say he's trying to say for all
It's
I,
for
yeah.
all I.
Oh,
Okay, so this is the vector space generated
Okay.
by those
I am all kinds
elements
of
for
confused.
all I.
Okay, wonderful.
Okay,
I understand now. Thank you.
it's not some quantum, I don't know what. Yeah, so,
Yep.
okay.
What algebras are A infinity and ACC?
What algebras?
Yeah, what kind of algebras?
Are they differential or something?
Hmm?
What kind of operations you have on them?
Okay.
Is A infinity an A infinity algebra?
So yes, you can endow A infinity with an A infinity structure,
Mhm.
but it doesn't have any differential. Okay, so it is actually an honest algebra.
Mhm.
Okay, but I didn't want to talk about the infinity algebras. Yeah, and the ACC, that's just an honest algebra. Yeah, that's maybe something that I should say. What's defined here? So we define I to be the algebra, the subalgebra generated by constant paths in the quiver. Okay, so another name for this is the ring of idempotents. Well, I guess F is the field with two elements. Okay. Okay, so now I think we're ready to define the category of curved complexes. Okay. Okay, what is a curve? So we start. So let C be the category of category with objects being I modules M, and if you want to make things easier, maybe find a dimension once.
It's not the same M.
It's not the same M. No, it's not the same M. It's not green. Yeah. Okay, and morphisms. Okay, what are morphisms? Morphisms from M to some M prime in this category C. Are just I module morphisms between M and this curly A, and maybe I should this A CC, but I will drop this CC from now on. So A is always this ACC. I've forgotten about A infinity. Okay, M prime. Okay, so morphisms are these I module morphisms from these I modules M to this tensor product. Okay, and then I should tell you what the compositions are. Okay, and well, you can't really do that much. So if you compose G and F, say F goes from M to A censored with M prime. Then you can say G goes from M prime to somewhere, maybe M double prime, and we get them out like this. And then we just take the identity on the first component. So identity tensor G. Okay, and then can't do that much. So we just compose these two first components. A tensor M double prime. So A. Okay, so far so good. And next I want to define a different, different category, so the preliminary category, so category of preliminary pre-complexes, if you want. So define this to be the category with objects. Well, the objects are pairs M, delta, where M is an object in C, and delta is a morphism in C, and an endomorphism. Right, and morphisms with category, so morphism from some M delta, M prime, delta prime. Those are just the morphisms of the underlying space. Okay, and obvious composition. And now what we'd like to do is we'd like to define a. My God. think in my next slide I'll become an architect for maths building. It's just horrible. Okay, so next I want to, so I want to define a differential on, turn this category into a differentially graded category to get our category of curved complexes. So, want to define some differential on morphism spaces. So let's suppose we have a morphism from M delta to M prime delta prime. Okay, then well, you do the usual thing, so pre and post goes. So D prime. Okay, and now you work out what the condition on this differential is, and on D is to be a differential. And what you get is D squared F plus F D squared. Okay, so you want this to be equal to 0. Okay, now of course you can just set these things equal to 0. Okay, but it turns out that, well, if you set it up like this, then it's also sufficient to ask for these structure maps to define, non-trivial D-squared relation. Okay, so now let CC be the full subcategory of C pre of objects M, delta, satisfying following relation, namely that D squared is equal to A tensor with the identity. Okay, and endow this with the differential graded structure given by the differential that we just defined, given by. Okay, and now I should tell you, I mean, this works in general for arbitrary A, where A, the only condition that we have to put on A is that it lies in the center of our algebra. But here, for this particular category, CC, I want to choose, so coming from such a quiver, I want to choose a particular A, namely I want to set A equal to the sum over all what I call elementary disk sequences. What is an elementary disk sequence? So that should be some algebra element. I think it's easiest to describe those elements in terms of these in these examples.
Are you working Claudius?
Okay.
Are you working Claudius?
Yes. Sorry. Yeah, I work over F2. I mean, but you can also do this. I mean, you have to figure out what the sign is. Right, so what are elementary disk sequences? Well, let's look at these examples. So what we do is we take our surface and an arc system cuts this surface into these disks. Okay? So now let's focus on one of those disks. This disk, so let's look at the boundary of that disk. Okay, and this boundary has some components in the boundary of the whole surface. And if all of those components are marked, then we can start on any given arc, on our arc system, and then walk around the boundary of that face. And that gives us a non-trivial algebra element. Okay, so we can just start here and then walk around. So P1, P4, P3, P2. Okay, and now this sum is over all faces and all such paths. Okay, so let's try to work out what they are in these two examples. So in this example here, A is equal to so what do we have? It's equal to row 1, row 2, row 3, row 0. Okay, so it's sum over all elements that looks like row 5 plus 3, row 5 plus 2, row 5 plus 1, row I. Over all I. Okay, let's call this variable equal to u in this particular example. And in this particular example, let's call the category that we get out of this the category of extended type D modules. Okay. This is my notation, just for the purpose of this talk. So, okay, so that's what David and Jonathan call these objects in this category. Right, and in this example down here, well, we have two faces, so we get two such two-domain summands, and in this case, A is equal to P to the 4 plus Q to the 4, where P is equal to the sum over all the PI's, and Q is the sum over all the QI's. Okay, so what does it look like? So P to the 4 is the element where you just start at some, say this arc here, and then you multiply P1, P4, P3, P2 together, and then start a different lattice. Different arc. Okay, and the category that we get out of this,
I'm confused. Why did we do the 4?
There's 4.
P to the 4.
Yeah, but is it the same thing that you take multiplying P with the same
Yes.
4 times?
Yeah, that's what happens.
Oh, okay, because of the relation, the strange relation. No.
Maybe that's how it works.
So you can also express this other guy as P to the 4 in the previous example.
You could, yes, yeah. Yeah, I guess so. Yeah, sorry.
Or
So
rho to the
for example, P1 to the 4th, that's 0.
Yeah, sure, but I
I
mean,
thought it is legitimate. In simple.
maybe we should talk about this afterwards. But I mean, there's just notation, and I promise you.
No,
P, P is the sum of PI.
Yes, no, but I don't then I was confused about there must be some other relation than that. Probably.
Yeah, I mean, it's a quiver algebra, so it
Ah,
comes from
okay.
all of the
The other
relations from the
relation
quiver.
dividing the quiver.
Yeah.
Okay.
So I mean, I can't compose P3 and P1, for example.
Okay, it's fine then.
Okay, great. Now, so I introduced some notation for this. So now it's time for a joke, I guess. So I call this category of peculiar modules. Okay. So the name really comes from these variables that are for these things, and those variables actually come from, I mean, those are the same that also Abbesident and others have chosen in their paper where they study the Fukaya category of punctured surfaces. So it's somewhat random, but I sort of like the name. Okay. Right. Okay. Now I have 15 minutes or so where I can talk about some applications of this and why I find these things, these categories interesting. Okay, so let's start with the theorem due to Jonathan Hanselman and Jacob from, I guess, earlier this year or late last year, that in this category of extended type D structures, modules, objects are represented or are classified by immersed curves. Immersed curves plus maybe local systems. I didn't remember what those are, local systems. in the surface in S2 minus in P2 minus a point. Yeah, that's it.
Somewhere you should really mention Haiden, Kontsevich, and Katzarkov.
Yeah, I mentioned that at the
This
very
theorem
beginning.
too.
Yes, so if you follow the arrows in the beginning, then they also had this. Yes, sorry. Yeah, so they also had this this classification. But sort of the point of this is that you go sort of directly to the Fukaya category and not by this category of twisted complexes. Okay. Okay, so that's theorem. And when in January I learned one of the workshops I learned a new word. So yes, I can now apply. So theoretic. Okay, so in this category of peculiar modules, the same is true. However, we have to replace the surface S2 minus 4 points. Okay.
What makes something a theoretical?
Well, okay, so I think I'm confident enough to call the argument that I have for the following statement. I'm confident to call that statement a theorem, namely that every object in the peculiar module, can be represented by an immersed curve plus local systems. Okay. However, the part that I still have to work out the details is that you that two immersed curves plus local systems represent the same or are homotopic if and only if they are the same.
Do these theorems recover the morphism at intersection points? Do these theorems also recover morphisms at intersection
Yes,
points?
so the first one certainly does, and the second one hopefully. Yes. So that's actually how I want to prove this the full classification. That I interpret the morphism space in terms of intersection points, and then finish the classification. Okay. Right, and the reason why I'm interested in particular in studying this case is because of the invariant, the tangle invariant that I mentioned at the very beginning. So that's it's not too late to start with a new definition. So a tangle, a ordinate tangle is an embedding of two intervals plus potentially this one union of closed circles into the free ball, such that you probably want the endpoints of the strings to lie on the boundary of your free ball. Okay. However, it turns out to be useful to fix a circle as some kind of parameterization on that boundary. Okay, and then we consider these embeddings up to isotopy. And then fixes this circle. Okay, so an example. So here we have there's three balls. And then we have this fixed circle. Okay, and then the endpoints of our tangle. And then let's draw some tangle. Okay. That's not what I want to draw. Okay, so here we have the 2 minus 3 pretzel triangle. Okay, and now the theorem is that from my thesis is that given a four-ended angle, C, we can associate with that this peculiar module, the bigraded actually. Which I denote as CPT. Okay, and the theorem is that this is invariant to homology. Okay, so this is an object in category of peculiar modules. Right. And you might wonder, well, why do we call it Tangle Floer homology? The reason for that is that, it comes from it's defined by Heegaard Floer homology, and the relationship to not Floer homology is as follows. So we can compute link Floer homology of the following link. So suppose we have two tangles, T1 and T2, and then we stick them together. Okay, and so we can, the theorem is that we can compute this from maybe a stabilized version of this from T D T1 and okay, up to maybe 3 stabilizations. Okay. Right, okay, and well, note that I haven't told you that the formula for this. So the conjecture would be that you can compute this, the link homology, from just looking at the morphism spaces between these two peculiar modules. And in examples, this seems to be true. However, the proof of this theorem relies on some on a computer calculation where I compute the bordered Suter homology due to Rowan-Zarev of sort of the bordered Suter manifold that sits in between these two tangles. Okay. And the actual result doesn't look quite as nice as you might hope for. So it doesn't really look like it's a morphism space, but it's still enough to give a gluing formula. Okay. And even without this this nice formula for the tangle for the gluing, we can still get something out of this theorem from the existence of gluing formula. Namely, the corollary is that mutation about the 2 minus 3 pretzel tangle leaves designated not the homology preserved. Okay, and in some cases it even preserves bigraded link homologies for certain orientations. Okay, and the proof of this is simply just a calculation of the peculiar modules. Okay, and then you realize, okay, the peculiar modules have a symmetry. Okay, and that allows you to give this to prove this. Okay, now in the last 5 minutes, I want to mention another application of this theoretic that I have erased here, unfortunately. Okay, so we can look at conjecture. So we can look at this algebra for this in this case for the four-punctured sphere, and we get can look at the quotient map. So we have this this algebra. I say specified as is with these four peculiar modules. We can look at the quotient map that we get by setting some pi equal to 0 and some qj equal to 0. Okay. And now the conjecture would be that that the function between the curved complexes, categories of curved complexes associated with these two algebras, induced by this quotient map is, and I'm not quite sure whether this is the right word that I'm using here, is faithful up to homology. So what I mean is that if you take two peculiar modules and set pi and some qj equal to 0. In other words, you in this picture down here, you set erase this here, and you make this component unmarked. Okay, and maybe do something similar here. Then you can have two curved complexes, and now honest complexes, honest IT modules on this side. Okay, and suppose they're homotopic. Okay, then this conjecture says that then they're actually homotopic the two complexes that you started with are actually homotopic. Okay, and if you have such a I think I have the basic arguments. I mean, it should follow from this theorem that I mentioned earlier. But if this holds, then as a corollary, you get sort of peculiar, you can compute CFTD from nice diagrams. Okay, and as an application or a corollary of that, we would get that mutation about general crystal tangles where you have 2n minus 2m plus 1, so you have an odd number of strands in one component and even an odd number in the other component preserves. Okay, and again, the proof is you compute, you just do this computation from nice diagrams, and then you realize, okay, it has this symmetry that is necessary for mutation. Okay. Maybe I just end with a picture, because I haven't really given any example of what a peculiar module looks like, or what these tangled invariants look like. So let me just give you. I'll show you what the peculiar module, or the loops, the immersed curves for this particular tangle look like. So let's draw this on the four-punctured sphere, okay, with this parametrization. And actually, these immersed curves, they have three components. Okay. So I draw them on separate four-punctured spheres. And the first looks like this. Okay. Third curve looks very similar. Okay. And the curve in the middle looks like this. Okay. And now if you want to do mutation, well then you see that it is mutation invariant, right? If I rotate this, then I get this picture. I might have to commute the curve. Get this picture, similarly, yeah, the other way around. And this, well, I mean, here you don't really have to think. This is the curve of a rational tangle. Maybe a rational tangle with two intersections, well, with two crossings. Okay, so that's also mutation invariant. Yeah, I think I'll stop there.
Questions? And local systems for these guys, or just integers, or
Oh, right, I didn't say what local systems are, so I wanted to. So local systems, the way you think about them is you have a curve, and you have a vector space on that curve, and then isomorphism of that vector space. In other words, you have a number of parallel curves.
Mhm.
Okay, then the dimension of the vector space, and then you might have some arrows going between those.
Okay, and these guys are one-dimensional or something, or what is the local system for these guys?
So here the local system is one-dimensional.
Okay.
So they're just.
So, I mean, presumably you can see the Hansen and Rasmussen and Watson picture from yours by going to the double branch or something.
Yes, so that's what I've started thinking about, but so far I didn't really see.
Oh,
That's not as,
I thought you were going to say that's obvious or something. No, but it's not.
that's not, I mean,
So yeah, you can compare these. I mean, if you look at these pictures,
Yeah.
right, you should get the trefoil knot, right?
Right.
But the trefoil knot has one. The curve for the trefoil knot has one component, and here you have three. So it's not really obvious what it should be.
and so, you phrased, so you phrased things in terms of peculiar modules, so you had to sort of fix a parameterization, sort of, that S1 gave you sort of fixed parameterization of your tangle,
Yes.
but like I could think about sort of the action of the mapping class group of the sphere with
Yes.
4 points on it, and,
Yeah, I think that would indeed be interesting. I mean, it should be just the
right,
the
you show that it's just, the action, this action on curves that it should be.
No, I think yeah. Until last week, I thought it was obvious, but no, you actually have to show that, and I haven't done it. No. But that might indeed be interesting because you have, I mean, here mutation invariance is just the symmetry, and in general for these invariants, you also get some symmetry. So, for example, you can show that the number of intersection points on each on opposite arcs are the same in each delta grading, but not in each bigrading. So there you already see bigrading mutation invariants fail. And then you even get something stronger, namely you get that if you just look at components of your curves that go from one fixed arc to a neighbored arc, then that number of curve components is the same as number of curve components on the opposite side. Okay, and if you have such a statement like this, that the action is the opposite action, then you could maybe prove a more general statement about the symmetry, because then you can, then you take some arbitrary curve that probably shouldn't intersect itself, and then you perform the action such that it just looks like such a curve segment, such an elementary curve segment, and then you know that, well, in the original picture that you started with, this curve, the number of those curves is equal to the number of curves that you get when you rotate those curves. Does that make sense? Okay, but I don't think that there's a general strategy. It can be a general strategy, because you can't always. I mean, you want a global symmetry, and the most that you can get is sort of this local symmetry for these curve segments that have to be reasonably nice, like that don't intersect themselves. So something like a curve like this, they couldn't apply this, I think. Does Liam have any questions?
Sorry. Let's thank Claudius again. We have cake if anybody wants cakes. Don't run away.